Hello, am I audible? Okay. And the screen is also visible, right? Because even while you asked for it, we will start with P3 first. So the problem was that we are given a tree and we have to find out a number of virtual trees. We have to count the number of one second. Count the number of virtual subsets. Where a subset is called a virtual tree subset if like whenever you have two nodes, this and this, then its LCA is also in the set. So this is a good virtual tree subset, for example. Okay, it is visible, right? Okay. So now we will first solve the. I will skip over the first two subtasks because they were pi is equal to I minus 1, which is just output 2 to the power n minus 1. All subsets are valid. And the second subtask was n less than equal to 8, which is just brute force all 2 to the power n subsets. Okay, so we start with the first subtask, which is s is equal to 0, which is basically output answer for tree. Okay, so how do we do this? Let's make some observations of some condition which holds for a good subset condition. Suppose that there are some more nodes here, some more nodes here, whatever. Suppose that this node X is not in subset. If this node is not in subset and we have two nodes over here and over here, like in different children, then this is bad. Why is this bad? Because the LCA is X, which is not in our subset. So this is a bad case. Now the other part is this, suppose that for all nodes which are not in the subset, this holds like only, so for all X not belonging to S, only one child has nodes belonging to S. This is necessary. Is this also sufficient? We can prove that this is also sufficient because you take any two nodes xy. Suppose its LCA is L, and if LCA is not in S, then LCA breaks the condition because two children has nodes. So this is both necessary and sufficient. For all x not belonging to the subset, only one children can have any nodes belonging to the subset. So this is bad. Okay, so now let's do a simple DP, which is like DPU is equal to number of valid subsets in the subtree of U. We have two cases. Case 1, a number of valid non-empty subsets. Case 1, we take U. We are writing out recurrence relation now. We take U, then children choice is arbitrary. Children can either be in children can either be in S or not be in S, and that will depend on them. Not like this part is fine. So we can just write the recurrence relation as DPU plus equal to product of children ways. Okay, so and note that here all the children are independent of each other. That's why we have written directly product. Now what is the number of children ways? That is simply product of dp v dp child plus 1. Why the plus 1? Plus 1 for empty. Yeah, dp child plus 1. Product of dp child plus 1. And the other case is u not in s. Then this will simply be some dp child as required. Why? Exactly one child has nodes in s, has nodes in s. So the final reconciliation can be simply written as dpu is equal to phi of dp child plus 1 plus summation of dp child. Phi is the product symbol for product. Okay, this solves s equal to 0. How to proceed further? Let's see subtask 4. It was that depth is less than equal to 10. This is giving us ideas that we need to somehow like we have to update a small number of nodes every time. What we do is that suppose like okay, so what the problem was that now we have to add nodes while maintaining the answer. Like we are, I hope everybody knows the problem at least, because otherwise you won't even understand what I'm talking about. So if the tree is like this and then we add this node, this is the new node, you can note that the dp is same. dp is same, the answers do not change for these nodes. The answer only changes of these nodes. The dp value only changes on the path from x to 1. So we need a fast way to update this. Okay, how do we do that? Recall the dp definition, which is like, so what you can simply do is that for each node maintain product dpv plus 1 of all children, of all children, and like summation dpv as well. And what you do is that, like, okay, you basically want the product excluding, you want product excluding this. Like when, okay, suppose we want to update the value of this node, then we have already gotten this node value and we already know this node value, then we need to update this. So what we will do is that we can here we can simply do it, but suppose there were even more children, like there is one child over here, another child, lots of children. Okay, I'll just repeat this whole section. So the first idea is that you only need to update on the path from x to 1, and that part only has 10 nodes over here. So we do not, so it will only be 10 updates. We just have to figure out how to do each update fast. Now how do we do each update fast is that we maintain product of dpv plus 1 in a segment tree, and summation of dpv in a segment tree as well. Then what you do is that when you get a query, you, like when you need to update, suppose you have updated this node and you want to update this node, then what you do is that you query for all the other children, you make one segment tree query, for all these children as well, like any other children it might have, make segment tree query and then update with this value. Well, segment tree is the way to avoid modular inverse over here. That's why I explained segment tree. What you do is you maintain dpv plus 1. Yes, yes, you can do it by you can do it using modular inverse, but segment tree is the way to avoid mod inverse. It will be a range query and then you can go for segment tree. Anyways, we'll move on to subtask 5, which is I think more interesting. It was that pi is equal to I minus 1 for all I greater than 5000. So here I'll explain the idea which kind of leads to full solution. First of all, for all I less than equal to 5000, solve in n square using subtask 3. Okay, so for now we need to only solve for all I greater than 5000, and this we must use this property that pi is equal to I minus 1 somehow, which is an interesting property. The idea that actually leads to the full solution, and there are some other ideas that you can do. Let's discuss the idea that leads to full solution. What happens is that, suppose this is the this is the whole tree that is formed by less than equal to 5000 nodes. Obviously there will be more part, I'm just showing a small example. And then we get this, right? The main idea over here is that the answer, see, all these extra nodes that got added, they modified this value, right? They modified dp of whatever this, let's call this node as x. They modified dpx. Because dpx got modified, the answer also got modified in some way. Answer got modified. And the thing is, you can represent the answer, looking at the recurrence, you can represent the answer as a into dpx plus b. This is the important part over here. If you know the value of dpx, then you're able to calculate you need to calculate this. I don't know what these values are, or you need to calculate a and b, but you can get certain values of a and b such that the answer is represented as a linear multiple of dpx. And once you have this multiple, you just need to find dpx. And what is dpx over here? It is 2 to the power whatever this thing is, 2 to the power k minus 1. So the answer becomes a into 2 to the power k minus plus b. I will not explain how to find a and b here, but you can do it. Okay, I guess I can explain it. Okay, here's a simple way to solve this. Like, how do you find these constants? Assume dpx is equal to 0. Find answer. Assume dpx is equal to 1. Find answer. And this gives you the answer. This gives you a and b, the constants. A proof of why this is true can be like, you can check the recurrence and how it works, and you will see that this is always true. But other than that, I'll just leave that for now. We move on to the last subtask, which is quite hard. By the way, can the people who solve this subtask let me know if the solution they have is also similar to this, because I don't know if it's simpler or not. Like, does it end up being similar anyways, even if the thought process is not the same? I'll wait for the response while I go on to the last subtask. Okay. We will work with, yes, the subtask 5 solution. Bro, even when you did not solve it. People did solve Hardwick. Like, at least there is some people in this meet. So what we will do is that we will create a new variable called increase answer equal to increase in answer increase in value of dpx after adding new child. Ah, okay. Okay. It's pretty similar to what I explained pretty much. Yeah. Okay. Increase in value of dpx after adding new child. After observing about the transitions, you can let me just directly show you the result that comes. This is the modified child. Let's call this node as u, this node as x, and these nodes as vi's. I will just directly write down the equation that comes. It is pretty easy to work out the math yourself. It will come as product of dp v plus 1 plus 1. There's a one extra plus 1 over there. Increase x is the increase in the value of dpx after adding a new child. And we get a recurrence relation like this. Yes, from top, from bottom to top, like from the child to the parent. The recurrence relation is from. Now the question is, how do we calculate these increase values fast? What we would ideally like to do, we would like to maintain qxu. One second. Qux, that is equal to product dpv plus 1 children of u not equal to x. Like if we maintain this quantity in some way, if it was possible to maintain these values, then obviously we could transition easily, right? Because you can just keep multiplying by the q values. But the thing is, we cannot maintain all of these values. We will do something simpler, like similar though. We'll maintain it for x is equal to heavy child of u. First of all, what is heavy child? uh this is coming from heavy light decomposition, which considered a vertex like this. Heavy child is the largest subtree. Is the largest subtree. Is the child with the largest subtree. So we will just maintain this quantity for x equal to heavy u, i.e. we are maintaining phi of dpv plus 1 v is equal to light child. Now, if we have maintained this quantity, then what happens is that it is well known that the part can be it can be proven as well that the part can be decomposed into log n distinct heavy parts. Suppose this is the one second. Suppose this is the node that got added, and then this is the heavy node of this is the heavy node, this is the heavy node, but the heavy node of this is this. So this forms a heavy path. This forms, like, basically going from this new added node till the point where it is no longer the heavy child. There will be, you only need to do log n such transitions where you go from a where you cross a light edge. So in this entire heavy path, what you want to do is just update the answers here fast. And then at when you want to go like this, update manually. if you were able to do this somehow, then you would solve the problem in like n log n into some constant into c, where c is the time for update. C is equal to update time. Since this subtask is really hard, I will not go into details, but I will tell you what the update needs to do, what you need to do eventually. After, you have to figure out the details yourself, because like it's not possible for me to cover all the details in this problem. One second, I'll just get the thing that I had written, what we needed to do. Okay, so we need to handle the following types of queries: update pi, point update on pi. What is pi and what is val I? I'll explain later. Like, you have to figure those out for yourself. I mean, val I plus equal to p1 into p2. Like, when you try to do the update, these updates fast, you will eventually get this problem. How I'm skipping the details. Find val I. We need a structure that can actually do this. And here the trick is that you will maintain a new value ai is equal to val I into pi plus 1 into pn. Then update pi, number one, update pi implies, by the way, like when you have to solve this yourself, because these will otherwise just seem random. You will have to work out the details of what structure you need to handle the heavy light operation, like the operations, the updates that you need over there. Once you understand that, then you will get this. This is what Sushil, when Sushil was trying this problem, eventually reduced to this version, and then he said that I cannot solve this. So I found the solution for this, how to handle all of these. We will do ai is equal to val I into pi plus 1 into dot pn. Update pi means that along with updating pi, we also need to do another thing. Notice that some values of ai also get changed. A1 to ai minus 1 get multiplied by constant. Prefix, suffix, product, and use distributive. I mean, the what you need to do is like you need to store linear functions in, not linear function, like ax plus b. Like it will become a range addition, range multiply, lazy segment. Like you will need a range add, range multiply, segment tree in the end. Why is it? Why did this get hanged? Hello, you can still hear me, right? Uh, okay, it works now. So once you reduce the problem to this, update pi becomes update pi, and ai to ai minus 1 will get multiplied by a constant. This thing val I plus, why did we even choose ai? It is to make this update easy. This update becomes easy. Now it just becomes ai plus equal to constant. And lastly, find val I. Just do ai into pi plus 1 pn inverse. You do need inverse for this, but there you can, like, that's why I gave the constraint of dividing by 0 is okay. Other than that, you it is possible to solve it normally as well without using inverse, but that gets much harder. So I'll just avoid it for now. This was the main idea, and I hope you understood the idea. The idea is updating a heavy path, like a heavy path altogether by chaining the updates together, while the light edge gets covered manually, gets updated manually, and there are only log and light edges. That's why this works. Let's now move on to P1, which was the easiest problem. What topics that are out of syllabus? Modular inverse is it out of syllabus? Even then, I have a solution without modular inverse. Also, by the way, just before people say by the way, that secondary product to avoid modular inverse is the secondary product to avoid modular inverse has in fact appeared in IOI 22 circuits. Okay, now we move on to A. What was A? A was we are given a constraint array A1, AN, and we need to construct a new array B, which is increasing, and BI not equal to AI. Minimize BN. Okay. So for example, for an array like 1, 2, 2, 3, 1, we will construct the array 2, 3, 3, 4, 4. This is an increasing array, and this also satisfies the other conditions. Minimum value of Bn is 4. So let's discuss subtask 3 directly. What you have to do over here is that you have to realize that you can follow a greedy strategy. Greedy strategy is what? Suppose bi is equal to x, then bi plus 1 is equal to x if ai plus 1 not equal to x plus 1 if ai plus 1 is equal to x. Basically, you will only increment x if needed. Yes, curd plus equal to ai equal to curd. Yes, sure. So it is pretty simple, like this greedy strategy. And why is this true? Like you, because it's greedy stays ahead type logic. Because like greedy is just always becoming optimal here. You do not lose out anything. One second. It is not a range alias problem. It cannot give a correct answer. You probably have something similar to range alias, but you do not. But you are telling me that is range alias. I will explain. I will explain binary search, not even binary lifting. Okay, so now we will directly go for full solution because the subtasks were like, okay, the casework, I can explain the solution. Those are mostly like ad hoc subtasks that you have to solve for each special case. Let's go for full solution. Notice what is happening in the above thing. Where did that array go? 1, 2, 2, 3, 1. We start with, let's start with 1 over here. Like we are starting, okay, this is B array, this is A array, right? This is A array. Now we are constructing B array. Let's start with 1 over here and then we will construct from here. Because 1 is equal, that's where we get 2 over here. Again, 2 is equal, so we get 3 over here. Then here we get 4. Here we do not get any update. And similarly, here also we do not get any update. And the final answer becomes 4. So what is the idea is that consider the range is L, L, then L, L plus 1, and L, N. The answers are clearly increasing, right? The answers are very clearly increasing. Okay. So let's store a different array, which is max right of V is equal to, wait, sorry, min right. Min right of V is equal to minimum R such that, yes, this code is like 10 lines, it's even shorter. Minimum R such that answer of L to R is greater than equal to V. Min R, we are storing a RV array which is like min RV is equal to minimum R such that the answer is greater than equal to V. If we can store this array, then it becomes a binary search. After we store this array, now how do we update this array? What the thing is that we need to also update this array, right? L can be anything. The idea is go backwards. Suppose you have the array for L and then you want to go to L minus 1. There are two cases. AL minus 1 is equal to 1 or AL minus 1 is equal to V not equal to 1. In here, you will just set answer of 1 is equal to L minus 1. Basically, that answer was this, sorry, min RV, right? Min R. Nothing else will get updated. Because an appearance of 1 does not change the other answers, it only changes the answer for 1. And this will make min RV is equal to minimum of min RV and min RV minus 1. You can see why this is true. Like whenever a value V appears, it essentially does not change the min RV values of anything except V. And it changes these in very predictable ways. After this, you will do a simple binary search, like you will sweep line in L order and then do a binary search. Since most people did a binary lifting for this instead, I'll also explain that. What we do is that from every x, we make an edge to the next occurrence of x plus 1. Did anyone? I think Popular Plus Plus did it. I think, and in testing also one person did it. I did not check a lot of solutions. So from every x, we will make an edge to the next position. This is a much simpler idea. Like idea wise, I guess this is much simpler and more standard. From every x, we will make an edge to a next position. So like this. And then if when we are given a query L to R, keep jumping while answer while do not exceed. Yeah, this would make every problem a tree problem. Sure, yes. This like keep jumping means that you basically go to the next point, X, Y, Z, and so on. Keep going. And there was a subtask given for this solution, which was AI less than equal to 100, where you could pre-compute all the values of next I and then just jump 100 times at most. And for full solution, use binary lifting. Binary lifting can efficiently give you how many jumps you can do. Okay, so this was P1. P2. P2, I will discuss the subtask of P2 because I like the subtask ideas as well. What was the problem, first of all? You are given a tree, weighted tree. find, yes, like yes, you have to take a decreasing size of jumps. It's as binary lifting. You can check out how to do binary lifting. So weighted tree, and we need to find pathway belonging to k to 2k. We need to just output yes or no. You should thank us, by the way, that we only gave you yes or no problem instead of also outputting the path. So subtask 1 and subtask 2, just brute force. Like, okay, what? Let's start with subtask 3. Line and NQ is less than equal to 2 in 20 power 5. What you do is that you can run two pointers, and for each left, like for each L, find minimum R such that sum of L to R is greater than equal to K. For each query, we do this for each query. And then since we have the minimum R, you can check that if this value less than equal to 2k, answer is yes. Otherwise, if for all a l this is bad, then no. Basically, since it's a line, you can just, it's APSP of acha, all path shortest path. Yes, all path shortest paths. I'll just tell the P2 as well, subtask 2 as well. Why not? So what you do is that you just want the smallest interval which is greater than equal to k, because it's like you only want to care about the smallest. If you get even one interval, it's good. So then you just solve the problem, because you only need to check if the smallest interval is less than equal to 2k. Yes, APSP, all pair shortest path. Okay, subtask 2 was n less than equal to 2000. For every I, run DFS to J to find distance ij. Sort all distances. This is n square. This is n square log. For query, binary search, first value greater than equal to k, check if this is less than equal to 2k. Did anyone use two pointers for the? Yes, a lot of people use two pointers. I think everybody did, like either two pointers, or you can do prefix sum plus lower bound, sure. But a lot of people I saw two pointers as well. See, here you have person. Naveen had full solution a long time before he actually submitted for full. And even before that, he was trying a subtask. Like he already had full solution, and we could see it from his code. But then he was solving a star subtask. I said DFS. DFS is O of n, and you do it n times. So it's n square. Okay, subtask 4. What is the given a star graph? By the way, this is supposed to hint towards full. Star graph is supposed to hint towards full. There are basically two cases here. Suppose some wi exists, k less than equal to wi less than equal to 2k. Like you can just take one edge and that will be good enough. Then answer yes directly. Yes. Okay, otherwise we need two different wi's. which means we need wi plus wj, k, and 2k. Now here is the idea over here. Consider maximum wi less than k. See, we know no wi belongs to the interval k to 2k. This is useful, very useful this is. Consider maximum wi less than k and second maximum. Then wi plus wj for this will be less than equal to 2k still, right? So if this maximum plus second max is also less than k, then bad, because no way can we find anything that is greater than equal to k if maximum plus second maximum is less than k, because like smaller things do not work. K to 2k there does not exist anything, and bigger ones you take, and greater than 2k you take, that is instantly bad. So it only leaves these options of taking less than k, so we should take maximum. So the problem becomes max plus second max greater than equal to k or not. And we can find max and second max with binary search. Next subtask. Yes, if max plus second is bad, I wrote bad as well, right? If less than k, then bad. And greater than equal to k means yes. Yes, your output no, yes. Like zero, your output zero, yes. Okay, subtask 5. Wi less than equal to 20. Another another subtask that is supposed to hint for full. The idea is that when k greater than 20, when k is greater than 20, the answer is yes, if and only if diameter is greater than equal to k. So let's prove this. Suppose diameter is less than k. Obviously, no, right? Otherwise, suppose diameter is greater than equal to k. Remove one of the endpoints. Let's call this as d. There are two cases. Again, that we will split it into two cases. My bad. D is less than equal to 2k. Okay, good. Otherwise, D is greater than 2k. Too large. Right? When D is greater than 2k, then it's too large. What should we do in this case? Consider this. You have some path with total length as D. Remove this edge. Consider this path. This is length D minus W. This is length D minus W. And since Wi is less than equal to 20, D minus W is still greater than equal to D minus 20. Reduces by less than equal to 20. Why is this reduction by less than equal to 20 useful? Because notice the interval k to 2k is of size greater than 20. Because this interval is greater than 20, keep reducing till you get d less than equal to 2k, and you will never and you will never overshoot and you will never overshoot in the other direction. So you can just keep reducing d till you reach this good interval of k to 2k. For k less than, like, this solves k greater than 20. So k greater than 20 implies check diameter greater than k. For k less than equal to 20, you can write a brute force. I will not explain how, but you can get a n a square solution for this. Can't you have d is equal to 2k plus? Okay, let's see. D is equal to 2k plus 1. So what we had, the constraint is that k is greater than 20. Then d minus w is equal to 2k plus 1 minus w. Okay. And we remember that we need to prove that this value is still greater than equal to k. Or equivalently, we need to prove that k plus 1 minus k plus 1 minus w is greater than equal to 0. Why is this true? This is greater than 20, this is less than 20. So obviously it's k is greater than w, right? K is greater than w, therefore this holds. Yes, sure. Let's go for the full subtask. Line case is pretty much a simplification of the full subtask, so we'll just go for the full subtask. So case 1. There exists wi belonging to k to 2k. Output yes. Wi belongs to k to 2k, then we know that the answer is yes. Otherwise, we use edges less than k only. We want, here we will again give a similar argument. Diameter of edges less than k if this value is greater than equal to k, good. Output yes. Otherwise no. Diameter of edges less than k, if this value is greater than equal to k, then good. Output yes, otherwise no. Why is this true? It will again go back to the same idea of wi less than equal to 20 subtasks. It's the same idea. The idea is that if you have a value 2k plus 1, which is the minimum value that exceeds the interval, and you only subtract at most k minus 1 to it, right? Like you can only subtract k minus 1 to it because all the edges are less than k. What will the new value be? It will still be k plus 2, which is greater than equal to k. So the subtraction will always be greater than equal to k. Like it will eventually reach, d will eventually reach k to 2k. So this is valid. This is the condition. Okay, it doesn't solve the problem yet because you will realize that this is not trivial to maintain. How do we maintain this? I mean, I won't say it's the main problem. It's like well known to everybody above, I guess, 2000 rating, or maybe even lower. I don't know. Even how Naveen did how when did you know this? Diameter merging. No, no. When did you know it? Like, and where, at what point of a CP journey did you know this trick? Green. Okay. Okay. Anyways, as you can see, it's a quite a common trick. What we'll do is that sort queries by k and maintain diameter of less than k. Then when we need to add one edge, Here is the idea. So add one edge is that you have one component here, component 1. You have another component 2 here, and you have some edge between them that is getting added. You have some diameter d1 over here. You have some diameter d2 over here. Why? Like he knows this pretty much. Acha, don't learn. Okay, yes, he should not have learned diameter merging before at green, of course. But whatever. The idea is that the new diameter, there are four, like some possibilities for the new diameter. It's either this, or it's this, or it's this path, or it's this path, or you can just consider all the possibilities. You're basically, the idea is that the new diameter is has nodes of previous diameter. There are two nodes here and there are two nodes here. There are four total nodes. Try all four, choose two possibilities. And this will become the new diameter. So you can maintain the diameter. Why does this work? Proof. Do I do? Sure, let's do it. This follows from the fact that, okay, so there are two cases. Let's draw the component 1, component 1, component 2, and the edge over here. Let's draw the diameters. So when the new diameter got added, there are two cases. Either this edge is useful or it is not used. There are two cases where either this is useful or not useful. So if this is not useful, what I mean is that the new diameter does not cross this. In that case, it is simply either this one or this one, right? If it's not useful, then it's either of these. And the other case is that when it's useful, that means that we will take some path till this, cross the edge, and go from some path again. Edge that is added, some path. These are paths, not just single edges. And since we want diameter, we want max path. And it is where known that max path in a tree is to one of the diameter endpoints. This is, I guess, a much more well known fact. And from this fact, we can prove the above claim. This also has a simple proof, and I'll not show it though. So after this, you get that you can maintain diameter like this. You will need binary lifting to find distances. Distances implies bin lifting you will need. But otherwise, this is the solution. Any questions? Yes, this is also one of the intended solutions, like realizing that you need to do log W times diameter. I cannot predict cutoffs. No, I do not think so. I think 236 will be cutoff for gold. I explained two solutions for P1. It's fine. I don't even know which secondary solution Naveen is talking about. Naveen can explain you the secondary solution. Arbitrary edge insertion and deletions. I'm not sure. Maybe it's solvable, maybe it's not. Arbitrary. Wait, P3. How does that even work? Like, you still maintain it's a tree, right? How does that work? You have to solve over all components or what? Like, the problem itself changes. Nishkars has the correct cutoffs. Yes, the diameter thing is the important part in P2. Implementation is not that hard. Like, it's totally solvable in like 20 minutes. If once, like, it's implementable in 20 minutes. Okay, then I'll stop the meet here. Thank you all for joining.